Hello and welcome to the module on dietary programming for optimizing athletic performance. In this module, we'll first look at energy systems, and that is the ATP producing energy pathways of the body that are dictated largely through skeletal muscle and the intensity at which we're working, as well as the fuel reserves available. Lesson 2, we're going to look at how to determine total daily energy requirements for athletic performance. Lesson 3, we'll look at fueling for strength performance. And lesson 4, we'll look at the age-old carbs versus fat battle for fueling athletic performance, and we'll look at some surrounding principles thereof. And then lesson 5 will be a nuanced look at the research on ketogenic diets and athletic performance. And we're going to finally close it out with practical application, which is a bunch of stuff. So this is a heavy-duty module. Let's get right into the first lesson. We'll look at energy systems, also called exercise bioenergetics. So if you look at the table on the right, we've got a continuum of energy pathways here. And as we go from the short duration maximal intensity, which the phosphagen system would predominate, then it just kind of goes down from there in terms of both ATP yield and the intensity that is applied to elicit the energy pathway. But duration goes up. And as we go along, longer duration, lower intensity, lower ATP production. And as this happens as we move from the phosphagen system through the glycolytic system, and then all the way to the oxidative system. More descriptions here. The phosphagen system is also called the ATP-CP system. And this fuels immediate and short-term singular or a limited number of repeated intense muscular contractions. And that's over here from 0 to 6 seconds of maximal intensity. And so the phosphagen system fuels activities. It's the predominant energy pathway in activities like short sprints, 1 to 200 meters, single maximal lifts and jumps, and throws, those sorts of sporting events. That's where the phosphagen system, aka the ATP creatine phosphate system, predominates. And then as we move down a notch in intensity and up a notch in duration, we're looking at the glycolytic system, which takes over, and it primarily fuels short to moderate term muscular work output. So this system is initiated very closely, a few seconds behind the phosphagen system. And it needs to be noted that anaerobic glycolysis and aerobic glycolysis are typically the two subtypes of glycolysis that are mentioned in the lay press as well as the academic literature, but those are actually misnomers. Okay, and I'll quote a review by Bakers and colleagues explaining why. So the entire glycolytic pathway is oxygen independent or anaerobic. More biochemically correct alternate names would be lactic glycolysis versus alactic glycolysis for intense and steady state exercise conditions, respectively. So the more intense variant of the glycolytic system involves lactic acid. And then as it gets longer duration, lower intensity, there is less to a significant lack of dependence on lactic acid, and therefore it's the alactic glycolysis system. So those are the two subtypes of the glycolytic system, which fuels high intensity activity lasting about 30 to 120 seconds. And then finally, we have the oxidative system, which is also called mitochondrial respiration. And this fuels longer term work output, typically associated with steady state, lower intensity, endurance type work. And so that's over here, the oxidative system predominates in lower intensity, longer duration over 3 minutes. And as we'll see, and as is important to note, the contributions of the energy systems, as illustrated here in this graph, they are sequential, but they're overlapping. So it's not like these energy pathways are activated on an on and off basis, because all the systems remain on, but have varying proportional contributions to ATP production. And this is going to depend on the intensity of the exercise, and that is dependent on both the endogenous or within the body and exogenous or from food or beverage fuel stores. And as you can see over here, this graph, the phosphagen system initiates everything. It's got the highest ATP output, but it lasts a very short duration, at which point the glycolytic system kicks in, and sequentially, but overlappingly as well. And then as the glycolytic system begins to wane and then exercise duration lingers on, then the oxidative system, aka mitochondrial respiration, becomes a predominant energy producing pathway. So when we look at what's called the strength endurance continuum, really we're essentially looking at the energy system continuum. So there's pure strength and power over here on the left side, and that would be much more representative of the phosphagen system. And then over here in the middle-ish, we have varying types of the glycolytic system, from the lactic glycolytic system to the alactic glycolytic system. They're all overlapping, they're all activated, and then that eventually goes into the oxidative system or mitochondrial respiration. But the big point I want to make over here is that most sports, most competitive sports, are a mix of strength and endurance demands in varying proportions. And I'm talking about varying proportions of these energy producing pathways, both across the different sports as well as within the sporting event itself. There's going to be a mix of energy demands across the ATP producing pathways across the sports and within the sports. So nutrition has to be individualized to reflect those demands. And that does it with lesson 1. I'll see you back on lesson 2, where we will look at how to determine total daily energy needs for maximizing athletic performance.